Okay, well, welcome
sounds
everyone.
good.
Yeah, welcome everyone. Today we're having a seminar from Austin Joyce from Amsterdam. He got his PhD in Chicago and was in Columbia, I guess as a postdoc, and he's going to tell us about cosmological correlators from the boundary. Thanks for putting up with our glitches, and we're very glad you're here.
Great, thanks again for the invitation. It's nice to be here virtually, and thanks for accommodating the time difference. I apologize for the troubles associated to it.
Your fault.
One nice thing about it, though, is it means we have like a nice small group, so this will be very informal. So I encourage you all to ask as many questions as you like. Feel free to interrupt me. I have a bunch of slides, but it's not particularly important to me that I get through all of them. So please feel free to interrupt at any time. So what I'm going to tell you about today is a little bit of work that we did recently with a great group of collaborators, thinking about how to construct cosmological correlation functions from a boundary point of view. And just to put us all sort of on the zeroth order same page, let me just remind you that cosmology is fundamentally a study of correlations. After all, we only have one universe. We can't make more of them in a lab and run experiments on them. Sort of all we can do is go out and look at the things distributed around us in the universe. So when we do that, we go out and look in the sky. We see objects distributed around. And the very interesting thing, which is remarkable, is that the objects that we observe, like galaxies and clusters of galaxies, are not randomly distributed in the sky, but in fact, their distribution is correlated. So in particular, if I go out and I find a galaxy, it's more likely to find another galaxy a certain distance away from it. And sort of this correlation or relationship is just captured in the two-point function or power spectrum of galaxy-galaxy correlations. And then what we do in cosmology is we trace these correlations through cosmic time, and by doing that, we infer the dynamics and contents of the universe. So for example, we can trace the correlations observed in late-time galaxies all the way back to the cosmic microwave background, where we can see that they originated as correlations in the temperature anisotropies measured in the CMB. You know, here's just a cartoon of the power spectrum of those temperature anisotropies. And so we can actually even trace these correlations even farther back, all the way to sort of the beginning of the hot Big Bang. So it's sort of this reheating surface at the end of the period of the early universe that we think was a period of inflation. And sort of the remarkable thing is that the further we trace these correlations back in time, the simpler they seem to get. So on this late time surface that actually provides the initial conditions for the hot primordial plasma that then forms the CMB, the correlations are really of a simple power law form of nearly scale invariant type. And a very interesting thing about them is that they appear to have been imprinted in an apparently acausal way, in the sense that points on the sky that have never been in causal contact appear to be correlated. So this is sort of a puzzle of early universe cosmology. You know, of course, this is a puzzle that by now there's a standard resolution to. But the thing I want to emphasize is that sort of the goal of early universe cosmology is to understand the evolutionary history that gave rise to these primordial perturbations. So I told you that cosmology is sort of the study of tracing correlations through time. And the goal of early universe cosmology is to sort of, you know, reconstruct a history that gave rise to the correlations that we see on this late time reheating surface that then grew into the large scale structures that we see in the late universe. And of course, the standard explanation or the standard history that we tell of how these correlations got built up is that we posit a phase of exponential expansion that we call inflation in the very early universe, where the background was very close to being de Sitter space. And sort of this explains through the dynamics of the spacetime how these correlations got imprinted, okay? And so for my purpose, the sort of important fact about inflation that I want to emphasize is that the correlations that we're interested in really reside on this late time boundary at the end of inflation. So we imagine there's a period of inflation. It goes on for a very long time. The correlations sort of get imprinted through the time evolution in this inflationary epoch, and then reheating happens, and the correlations frozen on that late time reheating surface are the things that then grow into the late time structure in the universe, right? And the important thing is that the local physics from the inflationary dynamics, or the thing that knows about what happened during inflation, gets encoded on this late time boundary.
Can I ask a question? Sorry, because I know
Please do.
I think we're going to be spending the rest of the time in de Sitter's space, and I'm happy with that. But I just want to ask if you have any response to the following question, which is, I know it's a bit off your what you're doing, but you know, it's always bothered me just a bit that when people make these kinds of arguments for inflation that you just made, there's never an answer to the question, well, what would it have looked like if it weren't inflation?
Mm-hmm.
In other words, you got to write down some state.
Yeah,
every
true.
state
That's
has
true.
some correlations. I mean, I don't want to go derail your whole talk, but you can think of it as a comment. You don't have to say anything.
All right, your criticism is completely fair, and there's sort of like, if you like, you could just posit some state. There's sort of nothing wrong with doing that. For me, sort of the compelling aspect of the sort of late time state that we observe is this near scale invariance, right? And so the near scale invariance points to there being some near time translation invariance in the sort of space-time that gave rise to it. And that implies something that looks a lot like inflation. So of course you can fine-tune things and cook up some other evolution, or you can just posit that that's the state. I give it to you because that's what it is. But yeah, at some point you have to, I guess, decide what you like. So for me, it hints that there's some nearly time translation invariant dynamics that set up these correlations, but I think reasonable people can disagree about how compelling that is.
Thanks. That's more than I deserve. It's more than I deserve. Go ahead.
Okay. So another nice thing about inflation is that inflation took place at very high energies, or it could have taken place at very high energies. We don't know precisely the inflationary energy scale, of course. And the fact that the bulk dynamics get imprinted on the late time boundary in some way tells us that measuring these correlations is an opportunity to learn about very high energy physics, because the energy density, or more properly, sort of the energy scale associated to the expansion rate, is very large during inflation. And so particles which have masses of order or less than that energy scale get excited by the inflationary background. They can sort of be produced on shell. And so inflation can sort of act like sort of a high energy particle collider, in the sense that it can generate very massive particles on shell, which then decay into the light degrees of freedom whose correlations we measure on the late time boundary. And we can infer the existence of these heavy particles by looking at subtle details in the late time correlations. And sort of one thing I want to emphasize is that the precise signals associated with the production and decay of heavy particles during inflation are somewhat challenging to compute. And so this requires developing new theoretical approaches to do this. And so that's sort of the, one of the motivating reasons for the type of work that I'm going to tell you about today. Although I won't emphasize too much this sort of inflation as a particle collider point of view, but I want to point out that it's sort of an underlying motivation behind what I'm telling you about. Okay.
Before going on, can I ask a very simple question? Can I go back to the previous slide?
Yeah, please do.
Yeah. So you're saying particles lighter than the inflation expansion scale can be produced.
Yes.
Do they have the same rate for different masses? I mean, what's the effect?
Well, yes.
I have the impression that if the particle mass is close to the Hubble constant, then the effect will be very large. And if it's much lighter, it's still observable.
Yes, that's right. Yes. Yeah, I mean, roughly speaking, you can think of it as being Boltzmann suppressed, where the temperature is roughly Hubble in de Sitter. And so things with masses of order Hubble can be produced like relatively reasonably efficiently and lighter, but things which are much heavier do not get produced very appreciably.
You mean for the lighter particle, there's no suppression at all? They're trying to say.
If they're sufficiently light, I don't think there's there's no Boltzmann factor, but yeah, there's a difference whether they lie in this so-called principal series of representations, so that their mass squared is heavier than 3/2 Hubble, or whether it's 9/4 Hubble, or whether it's lighter than 9/4 Hubble.
Okay, sure. Okay, let's go. Thank you.
Does that answer your question?
Yes, sort of. Yeah.
Okay. Yeah. So, like I said, the computation of these signals is somewhat challenging, and so we're motivated to think of sort of new ways or new theoretical tools to approach these calculations. And an important feature of the inflationary epoch, which is sort of related to Marcus's question, is that we have no direct observational handle on the inflationary epoch. Really, what we do is we infer its existence from the properties of the correlations that we sort of measure on the reheating surface. So we sort of infer that the inflationary epoch is there, but we can't image it directly. But that actually sort of suggests an approach to compute these observables. The fact that we have no direct way of seeing this inflationary epoch sort of suggests that, okay, maybe we should think of a way of calculating things or constraining things that doesn't make explicit reference to the actual inflationary dynamics. So can we try to just write down the final observables which live on this late time boundary on the late time boundary itself? Okay. And one reason why you might imagine that that's possible is that it turns out that the final answers are very strongly constrained by things like symmetries and locality on this late time surface. But of course, the challenge is kind of twofold. Like, we don't know the precise encoding of these sort of cherished bulk principles in the boundary observables. So our understanding of sort of the rules of the game of cosmological correlation functions is still somewhat primitive. And so we first have to kind of learn the rules a little bit, and then we can try to use these rules to constrain and construct correlation functions from some sort of bootstrap type of perspective. And so philosophically, this approach is kind of similar to the S-matrix or conformal bootstrap programs, where you construct observables directly based on consistency requirements. But I would say, of course, it's much less mature. We're sort of just beginning to learn what the rules are and to use them to calculate things. Okay. So now I think is probably a reasonable time to stop and ask if people have any questions about the sort of introductory / motivational stuff. Okay. If everybody is happy. Oh, yeah, please go ahead.
Sorry, I was muted when I started. I'm going to be very interested to hear how you're defining this boundary. If I have some classic slow roll inflation with a steep potential, I know what it means. In a more general context, I'm very interested to see how you're going to use that, define that concept, or so maybe it's. I'm sure you'll talk about that, so maybe it's more.
Actually, I'm not going to. I'm going to entirely not talk about that. So I think for that purpose, you can think of everything as happening in exact de Sitter space. And so what I'll mean by the boundary is always the space-like asymptotic boundary at sort of conformal time goes to 0.
Oh. So I had the impression you were trying to generalize beyond de Sitter, but maybe that's. But if you're talking about de Sitter and in the end of inflation, I'm happy with that. I thought you were trying to generalize that.
Well, at the moment, I'm just telling you things about de Sitter. So it is true, of course, that during physical models of inflation end, and so the universe is not exactly de Sitter, but it's some quasi de Sitter. And I will comment briefly on how you can take the de Sitter invariant expressions that I will tell you about, and how you can deform them to construct sort of the leading order and slow roll correlators, where we still sort of know what we mean by the inflationary boundary. For spacetimes that are very far from slow roll, I'm not gonna say anything about.
Okay, thanks.
Okay, no problem. Okay.
So I have one more question, if that's all right.
Yeah, sure.
Will you comment anything about initial conditions? Because that's another thing that sometimes comes up with, like, I don't know, inflation and whatnot.
Yeah, we'll have just a sort of small comment about initial conditions, but we can talk about it more afterwards if you want.
Cool, thank you.
But to sort of 0th order, I'm going to assume Bunch-Davies initial conditions. But of course, I have to tell you what that even means on the boundary. So if I'm not going to talk about the de Sitter space directly, I have to sort of tell you where that information about choosing the Bunch-Davies vacuum gets put in. And I'll point out where that piece of input goes in.
Thank you.
No problem. Okay, good. So here's sort of the rough outline. So first I'm going to tell you a little bit about sort of the singularity structure of cosmological correlators, because it turns out that this is actually a useful handle to get sort of a first grip on what these objects are. But then I'll try to explain that, the things we're actually interested in are the full correlators away from these singular points. And so we need to understand how to extend away from these singular loci. And I'll explain a couple ways that we can do that. One is to use the symmetries of the de Sitter background. And another is to kind of use things like bulk unitarity and locality to try to extend away from these singular loci, which turn out to be more useful for correlators involving spin, as I'll explain. Okay, so as a first step, let me just try to briefly describe what the singularities of cosmological correlators are. And so first, let's take a step back to take a step forward. And let me just remind you of sort of a lesson learned from a philosophically similar program, sort of the S matrix bootstrap point of view. So of course, in particle physics, the fundamental observables, so sort of the analog of correlation functions in cosmology, are scattering amplitudes between sort of plane wave-like particle states. And there's been a huge amount of progress in recent years bypassing the sort of traditional Feynman diagram techniques in order to just write down these asymptotic observables that kind of live on null infinity of Minkowski space directly using consistency constraints or physical principles like locality and unitarity. And from sort of the success of this program, you could abstract many different lessons, but I'm going to just sort of pick the one that will be most useful to me. And the lesson I want to abstract is that a lot of the physics of scattering is actually controlled by singularities. And so, for example, if I have some scattering process, we know that at least at tree level, the only singularities that this process is allowed to have are when some subset of the momenta actually go on shell. And we know that sort of what's happening there is that a particle is getting produced and propagating a long distance in spacetime. And so the amplitude for this process kind of splits and factorizes into some sub-amplitudes with sort of a propagator-like factor in between, okay? And so if I just demand consistent factorization of amplitudes, it turns out that I'm basically putting in all the information about the singularity structure and their residues. It's not really surprising that this is very constraining. It in many cases completely fixes the amplitudes for certain particle content. And of course, a famous example of this is something like BCFW, where you can use complex analysis to reconstruct the full amplitude. Okay, so what we want to do is to kind of abstract that lesson and apply a similar philosophy to cosmological correlators. So here I have to apologize to you. So I've been saying correlator for, I don't know, the last 20 minutes or something, but I'm going to pretty much always be talking about the wave function rather than the correlator. And of course, these two objects are closely related, but let me just explain sort of the precise object that I'm interested in, and then I will go back to totally abusing terminology and using the two words interchangeably. So the object that I'm going to be interested in is the cosmological wave functional. So we don't often think of field theory in Schrodinger picture, but actually it's in some senses more natural in cosmology. And so the object I'm interested in is, you can just think of it as the projection of, whatever the bulk state that I'm interested in that sort of has undergone some time evolution. And I'm going to project it onto some Heisenberg picture field states on some time slice, right? And then I can think of this state, it's like the interacting vacuum state. So it gets built up by a bunch of processes in the bulk. And then on some time slice, I can project it onto whatever set of states I like and write down a representation for it. So here, the natural choice of bases are field eigenstates on this slice. And then this wave functional provides a probability distribution for field profiles on this time slice. And so exactly like in quantum mechanics, if I want to extract a correlation function at this time, I just take the wave functional, I square it, multiply by a bunch of operators, and integrate. Okay, exactly the same way I would do in quantum mechanics. Okay, so again, oh, sorry, is this frozen? Can you see this? Okay, so I'm going to only be talking about perturbation theory, and in fact, I'm only going to tell you things about tree level today. So in perturbation theory, the wave functional is actually quite simple. It turns out it's really just the on-shell action. So it's just the action evaluated on some classical solution with the prescribed boundary conditions that I'm interested in. And in perturbation theory, it has an expansion around sort of a Gaussian. So here is just the Gaussian piece, and then I can write it as an expansion in these late time field fluctuations times some kernels. And these kernels I'm going to call the wave function coefficients. And these wave function coefficients really contain the information about correlations in the late time state that I'm interested in. So if I hand you all these kernels and I tell you, this is a perturbative wave function, then you can reconstruct all the correlators you want by just integrating. Okay. And of course, exactly the same way that we do in particle physics, these wave function coefficients can be computed in a Feynman diagram-like expansion, which also should be fairly familiar from ADS-CFT, which has a sort of similar structure, where you can think of psi as being the analog of the CFT partition function computed like as the on-shell action in ADS-CFT. Okay. So in order to get some intuition for the singularities of this object, it's actually helpful to just look at a very simple toy example and kind of stare at some Feynman diagrams and understand the structure they have. Okay, so the simple example that I'm going to focus on is really just phi to the n massless scalar field theory in flat space. And we just want to think about this a little bit from the Schrodinger picture point of view. Now, I want to just think about computing the wave function on some time slice in perturbation theory. Okay, so what I'm doing is I'm basically computing the on-shell action. So I have to specify some Dirichlet-like boundary conditions on the time slice that I'm interested in. And then once I've done that, I want to solve for the perturbative objects that I need to reconstruct the classical solution that I'm interested in. And it turns out there are basically two types of propagator that I'm going to need. One is sort of the classical solution to the linearized equations of motion, which it should not be surprising is just a plane wave. And this is really the flat space analog of the bulk to boundary propagator in ADS-CFT. And then the other thing that I need is the analog of the bulk to bulk propagator, which is the bulk Green's function subject to the Dirichlet boundary conditions that I'm going to place on this final time slice. Okay. And it turns out this bulk to bulk propagator has a piece which is very familiar, which is just the normal Feynman propagator. And then it has a piece that imposes or enforces the boundary condition that when I take either T1 or T2 to 0, that this propagator vanishes. And so I've normalized things such that this boundary sits at T equals 0. So the bulk to bulk propagator vanishes when you take one of the points to the boundary. Okay, and that's just to ensure that the boundary conditions that I'm imposing continue to get obeyed by the nonlinear solution to the equations of motion. Okay. All right, so with these very simple perturbative rules, we can just start computing some examples. The simplest example is if I have like a phi cubed interaction and I want to compute a like a contact diagram. So here I just have 3 bulk to boundary propagators. So I just am doing an integral of an exponential. Should not be surprising. I just get something that's like 1 over. Here, this k is really the sum of the square root of the momenta squared of these external lines, which I will just call energies in a slight abuse of terminology. So it's really analogous to the energy carried by these external lines. Okay, so that's sort of the simplest possible example you can imagine. The next simplest example is if I have an exchange. So if I have an exchange, the relevant integral that I need to do. So here, let me just remind you that, yeah, we're not used to doing this sort of partial Fourier transform, but I've Fourier transformed the spatial directions, but not the time direction, because I want to pick out some particular time slice as special. And so I need to integrate over the position of all of these interaction vertices.
So can I ask this k that you're calling energy? It's somehow the momentum that's conjugate to translations in some conformal gauge or something. I mean, can you just say a little bit more about what this k is? I mean, because you're not writing down what the metric is. It's there's some metric that makes it look, yeah, those k's. There's some metric that makes it look much like flat space, right? Some way of writing it. And
yeah, sorry, maybe. Sorry. To be clear, everything I'm showing you on these 2 slides is literally.
Oh, this is flat space. I'm sorry. That's right. Okay.
Yeah.
Never mind. Then I know what it is. Sorry.
So yeah, so it should, yeah. So you're exactly right. It looks a lot like flat space because it is flat space. Yes. Okay. Yeah. So the reason I'm showing you these formulas is to like get some intuition, just showing you some simple flat space examples, and then I will argue that things are fairly similar in de Sitter space in a moment. Okay. Yeah, so here's the simplest example that's just like some contact correlator. And then here, this would be the wave function coefficient or correlation function that you would get from the exchange of a particle. Here's sort of the relevant time integral. You would integrate over the insertion points here with some bulk-to-bulk propagator between them. You can just do the integral. You find out it takes this form. So it depends on sort of the total energy involved in the process here. And then these you can think of as kind of the energies associated to these left and right vertices. Excuse me. And the only thing I want you to abstract from this slide is that these correlation functions or wave function coefficients are singular when the energies flowing into a vertex add up to 0. So when the partial energies are conserved, the correlator is singular. Okay. And we can kind of understand that in the following way. So let's go back to this like really simple contact-like example. So the type of integral I need to do is just an integral of e to the I. Here I'm calling it E as like the energy flowing into this vertex times t. And I'm integrating this thing all the way from -infinity up to 0. And we can kind of understand that this thing is diverging when E is going to 0 because the limit of integration is running all the way off to -infinity. And so the singularity is kind of localized at t goes to -infinity. And it's singular precisely because the domain of integration is infinitely big. And we're not getting any oscillating suppression when E is exactly 0. Okay. And we can kind of understand that, okay, so there are some caveats that are not particularly important at the moment. So for our purposes, all correlators have this singularity. And one way that we can understand that, and one way we can understand sort of what the singularity is by noting that when we're doing this type of calculation, we're doing almost exactly the same thing that we do when we compute scattering amplitudes, although in kind of a peculiar way. I could compute a scattering amplitude in this sort of like half Fourier transformed way, where I choose to integrate over time, but integrate or Fourier transform with respect to all the spatial momenta. And I would find that this time integral, what it's doing for me is generating a delta function that demands that energy is conserved. And then obviously the thing it multiplies will be a scattering amplitude. But here, since I'm interested in something evaluated at some time slice at t equals 0, I only integrate over half of the space. And so rather than getting a delta function, what I get is some like 1/e pole. But nevertheless, the thing that it multiplies is still the scattering amplitude. And so particular, when I go to this E equals 0 locus, the residue of this 1/e pole is going to precisely be the scattering amplitude. And beyond that, we can kind of think of this 1/e pole as itself being a signature of some particle interaction at a point. Like, so when the energy gets conserved, you know, the fact that these particles came together at a point leads to a singularity in the correlator. Okay. But so contact-like correlation functions only have this total energy singularity and don't have any other singularities. But correlation functions that arise from exchange can also have other singularities.
So,
and one way to understand that, sorry?
So I can ask a question. So is this,
Yeah, please do.
this looks like it's precisely equivalent to just doing Hamiltonian perturbation theory. In other words, if I just did ordinary quantum mechanical Hamiltonian perturbation theory, I would get exactly these kinds of energy denominators. It looks like exactly the same thing. I could just ask for the do the perturbation theory for the wave function at some time. I put in some I epsilons to turn off the evolution, the interactions at early times, right?
Mm-hmm. Yes, yeah, you can. And in fact, that actually leads to some like beautiful recursive formulas. So this model is like extremely simple. So you can basically compute anything you want in it. And sort of taking the approach that you are suggesting, sort of doing like old-fashioned perturbation theory on the late time boundary. Yeah, you can derive some very beautiful recursive formulas that compute these correlation functions in a very simple way. Yeah, and in fact, you can understand these total energy singularities in exactly the way that you're saying. That's right.
Because I'm doing some work on Hamiltonian truncation of quantum field theory, and we developed exactly this. So we reinvented the wheel using exactly this perturbation theory in this Hamiltonian language to match onto the truncated theory, which is, it's not exactly a late time boundary, but that turns out to be the correct way to match onto the truncated theory. Anyway, I'd be interested. I'll ask you maybe if we have a few minutes after your talk. I'll ask some more about that. But thanks.
Sure. Yeah. Okay. Yeah, that's very interesting. So that's something that's a bit special about flat space. Things are not quite as nice in de Sitter. I'll try to explain the difference when we get there, but if not, I can tell you afterwards. But that it's very related. And in fact, so this stuff is pointed out in this really beautiful paper by Nima and friends. Okay, good. Yeah, so like I said, these contact correlators have only these total energy singularities, but exchange correlators can have singularities at other loci in kinematic space. And one way to understand that is that there's sort of now multiple time insertion points that I have to integrate over. And like I told you, the divergence is really coming from these integrations running off to -infinity. So I could imagine, dragging this point off to -infinity and seeing where the singularity is, but leaving this thing at some finite time. Okay. And I can even figure out what the coefficient of this singularity should be like, because I know that, the really non-trivial part of the time integral is coming from this bulk-to-bulk propagator. And I know exactly what it looks like in the limit that one of these points goes to -infinity. It just takes this kind of simple form. If you remember, it's like the Feynman propagator plus another piece. And so in the Feynman propagator part, one of the theta functions is just always 0 when one of the times is strictly earlier than the other. And so you get a difference of these two terms. And you can see that one of them has plus the energy of the internal particle. One of them has minus the energy of the internal particle. And so what you find is that, this just looks like a plane wave factor for the internal particle. And so the residue of this singularity, when say the energy in this left vertex adds up to 0, has a factor which is just the amplitude associated to this same process over here. And then the difference of two wave function coefficients associated to the right vertex. And so you see that in the limit that the partial energy of one of the vertices adds up to 0, the residue of that singularity is just an amplitude times a difference of two wave function coefficients. But the sort of interesting thing is that the residue is given in terms of 3-point data. And so you can figure out what the residue of this 4-point object is knowing only 3-point data. Okay. And sort of, for my purposes, maybe the important thing will be that the presence of these partial energy singularities, you should really think of as a signature of tree level exchange of a particle. So if I handed you a random object, by looking at its singularities, you can kind of infer a little bit about the type of bulk process that gave rise to it. If it had these exchange singularities or these partial energy singularities, you would know that it came from a bulk exchange of a particle. Okay. So actually so the model I'm describing to you is like so simple that many things are actually totally fixed already by the singularity structure. So at 3 points, it's essentially trivial. So I've told you that this thing has a 1 over total energy singularity. That singularity is the residue, or sorry, that residue of the singularity is the corresponding flat space scattering amplitude. It turns out that just totally pins down the object to just be 1 over the total energy. Okay. It turns out that this is actually a slightly non-trivial thing to satisfy at 4 points, because now there are 2 different partial energy limits I can take. So I have some object and I want to demand that when the energy associated to the left vertex goes to 0, that it takes the following form. It looks like the left amplitude times this shifted right wave function coefficient divided by the left energy. So the way I'm writing it, K12 is just K1 plus K2, and S is the energy of the internal particle. So this is just the singularity that I want. And then if you go ahead and just compute this shifted 3-point wave function, it just turns out to take this form. Okay. And then I can do the same thing for the right vertex, and it's exactly the same, just interchanging K12 and K34. And I see it takes this form. And then the challenge is to find an object that in each of these singular limits reduces to these factorization limits, right? And so it's just sort of a math problem now to find a function that has those properties. It turns out there's a totally unique answer. It turns out this is the unique answer. And the reason is that you have to interpret these kind of funny singularities with a minus sign as being the total energy evaluated in a particular kinematic limit. And another rule is sort of we don't want these folded-like singularities. So they correspond to kind of a particular folding of the 4 points associated to this correlation function. So we call them folded singularities. So I don't want those things to be the answer because they don't have a physical interpretation. So if I demand those things are not there and that everything has the right factorization limits, sort of the entire answer is pinned down. And the interesting thing is you're forced to introduce this total energy singularity whose residue is just the 1 over S scattering amplitude that you expect. And so if you're familiar with this kind of 4-particle test in the S matrix at 4 points, this has kind of a similar flavor to that, but here we're really just talking about like a single S-channel diagram. So there's already some kind of interesting factorization constraints for even just a single channel diagram of these correlation functions. Okay. So just as sort of a summary of what I just told you. So I'm mostly going to tell you about 4-point functions today, although we can talk a little bit about higher point functions if you're interested. But the 4-point function is really controlled, at least at tree level, by these 3 singularities that I just described. It has a singularity like all correlators do when its total energy adds up to 0, whose residue is just the 4-point scattering amplitude for the same process. And then it has these partial energy singularities when the energy associated to one of the exchange vertices add up to 0, whose residue we totally know. It's like a scattering amplitude times a difference of 2 3-point wave functions associated to the other vertex. Okay. And so we're going to try to use this information to learn something beyond this simple flat space example. So it's at this point I have to ask you to take like a small logical leap with me. So here I've just showed you a very simple example where sort of we can calculate everything and you can just stare at it. But what I want to do is to promote this singularity structure to a principle. So I want to say, okay, now I know all correlators, even away from flat space, should have this like total energy singularity. I think its residue should be related to the scattering amplitude. And then I expect that exchange correlators will additionally have these partial energy singularities, and that there won't be any other singularities at tree level. And then I want to sort of see how far that can take me. And let me, not ask you to blindly take this leap with me. Let me try to give you some intuition for why you might believe that this kind of thing could possibly be true. So remember, in de Sitter space, as I go to very, very early times, I can think of modes as shrinking, right? Because de Sitter space is expanding. It's sort of stretching modes as time goes on. So the time reverse of that, modes are kind of shrinking into the UV as I go very far back in time. And so it shouldn't surprise you a bunch that modes look a lot like they're in flat space as I go to the infinite past. Again, this is kind of an assumption that I'm working with Bunch-Davies initial conditions. Otherwise, things can be a bit funnier. But with that assumption, the sort of mode functions for particles in de Sitter space in the far past look a lot like their flat space counterparts. And then there are sometimes some factors of conformal time. And since we're doing time integrals, these factors can change the precise nature of the singularities that appear. So sometimes I don't get simple poles, sometimes I get higher order poles, or sometimes I get logs or things like that. But the existence of some singularity is robust, basically because when the total energies add up to 0, I'm still no longer getting this exponential suppression. And so something is going to diverge. Okay. But so far, I've really only told you about some very special loci in kinematic space.
Sorry, can I ask about the intuition?
Sure.
In de Sitter, should I be thinking of these singularities as arising when they're arising from the region where these points are going very far into the past? Yes.
Yeah, although it's a little tricky because
Well, because
but only
that
at
conflicts with my
sorry,
intuition that somehow the past is like the UV, right? Because this thing is expanding until you get to the boundary. And so somehow there's an opposite intuition that I would have that might just be wrong. That's what I'm asking about, that somehow early times just don't matter. Things just get washed out, and it's all sort of happening in the last Hubble before the boundary. Is that intuition just wrong?
it's a little tricky because in order to actually access these singularities, maybe I should have said this, but they cannot be accessed for physical momenta. You have to analytically continue to complex momenta in order. So for example, I'm trying to make the energy add up to 0. I can't make that happen for physical momenta.
Right.
So I need to go to some sort of complex configuration in momentum space, where it turns out at that complex configuration, the contribution is coming from these very early times.
Because I'm trying to see if there's some picture, like in the S matrix, there's a picture that these singularities have to do with, real intermediate states, which are, I want to say, are IR stuff. Okay, and then there's all this UV stuff. For example, it has to do with renormalization, but because it's UV, it doesn't make these physical singularities. And so I can have some picture where I can sort of separate the UV from these singularities. And maybe I'm trying to shoehorn this into that and trying to think of the very far past as the UV, but you're sort of saying that doesn't work like that.
I mean, there is a sense in which it kind of does work like that. So yeah, to be totally to be like totally precise, when I analytically continue the energies to go to the energy equals 0 locus, the residue of that singularity is a scattering amplitude, but it's a scattering amplitude sort of in the high energy limit in flat space. So in that sense, it's sort of like as you go to the UV, you are accessing some, or sorry, as you go to the infinite past, you are accessing some UV information. but it's not quite that this UV information just gets washed out by the later de Sitter evolution.
Right. Okay, sorry, go on. Good. I want to hear the rest of your story, so thanks.
Sure, yeah. Okay, but yeah, the only thing I want to emphasize, or at least give a plausibility argument for, is that you should at least expect these singularities to also be there in de Sitter correlators. And I'll show you some examples where that just is the case. Okay. But of course, yeah, so as I just mentioned, the things that, the things I'm just telling you about these singular limits of kinematic space cannot be accessed for physical momenta. So of course, the things we actually care about are not the correlators in these particular limits. What we want to do is to sort of extend away from these particular kinematic configurations to physical ones and sort of get the full correlation function, okay? So there are at least two reasons why this is kind of non-trivial. So one, this is maybe slightly more phenomenological, but in sort of phenomenologically interesting models of inflation where the inflaton really knows that de Sitter is going to end, typically the interactions of the inflaton, because it's a Goldstone, are not de Sitter invariant. And so despite the fact that the background may be very close to de Sitter space, it could be that the interactions themselves actually break de Sitter invariance. And so knowing something about some singular locus may not be enough information to sort of extend things away from that particular point. And maybe more importantly, in situations where you really produce like honest to goodness, very massive particles in de Sitter, it turns out the analytic structure is much more complicated than just poles. There can be branch cuts and things like that, and you have to sort of understand where these cuts go away from just some singular loci, okay? And so what we need is some tools to understand how to extend these correlation functions away from their singularities, okay? Yeah, and also related to Marcus's point, let me just like sort of remind you that another reason you want to do this is we want to understand how correlation functions change as we sort of change the shape of the points that we're trying to compute the correlation function of. So here, it's always convenient in cosmology to go to momentum space. And so the correlation function is really a function of sort of four momenta who have to add up to 0 because of spatial translation invariance. And then we can ask questions like, how does the strength of correlations change as we change the shape of this quadrilateral? And sort of one of the beautiful features of inflation is that the time evolution of the inflationary spacetime gets imprinted in the shape dependence of correlations as you vary the shape of this quadrilateral. And the reason for that is just essentially that modes freeze out in de Sitter space. And so modes that froze out earlier are kind of longer wavelength. And so by changing the shape of the quadrilateral that you're trying to compute the correlator of is probing different epochs or different relative times between the modes in the inflationary spacetime. And of course, that's the type of thing that we're really interested in. So we want to, measure these correlation functions in the late time boundary because we want to learn something about the bulk physics. Okay. All right, so what are the types of ways that you could imagine moving away from these singularities? So I'm going to focus mostly on the first one, but I'll say a little bit about the second one later on. So roughly speaking, we have...
Sorry, can I just interrupt? This may be sort of a more phenomenological question, but I mean, I thought that a lot of focus was on the 3-point function. And it seems like that's something you can measure. You can't measure the 4-point function unless you can measure the 3-point function, right?
That's correct.
Are you just talking about the 4-point function because less is known about it theoretically, or could you just say something about why are we focusing entirely? Why are we not talking about the 3? I know it's 0 essentially in your model, so that's a good reason. But other than, can you just say more about why are we talking about the 4-point function?
Yeah, so right now, the reason we're talking about the 4-point function is just because it's sort of cleaner to talk about. Just sort of everything is much simpler to talk about exchange and stuff like that. There's another sort of phenomenologically motivated reason, which is that at the level of sophistication I'm telling you everything is happening in exact de Sitter. But it turns out that if you're interested in the slow roll inflationary 3-point function, that thing is actually easily generated from an exactly de Sitter invariant 4-point function. So it turns out there's a very easy way to take the 4-point objects that I'll show you in a minute and deform them in order to generate the slow roll inflationary 3-point function, which is the type of thing you would care about for phenomenology. So part of it is just for simplicity. The other part is that actually, in some sense, it is, at least in slow roll inflation, the more fundamental object. It turns out that slow roll inflation, many of the things about the 3-point function are secretly governed by de Sitter symmetry of a 4-point function. Okay, which hopefully I will have time to show you more explicitly. Okay, yeah, almost surely I will not have time to tell you about this, but there's kind of an interesting story about factorization and sort of cutting type stuff involving rational correlators. So there's sort of a vague, yeah, at least the feeling I kind of get doing these types of calculations is that tree level stuff in de Sitter is kind of philosophically similar to loop level stuff in the S matrix. And so it shouldn't be surprising that some sort of cutting kind of stuff is a useful way of thinking about tree level exchanges in de Sitter. Okay. Yeah, maybe now I can just stop and ask if people have questions about this part.
Yeah,
oh yeah, maybe sorry, go ahead.
Yeah, but on this slide, you say this for rational correlators, you have imposed consistent factorization plus unitarity. Is it consistent factorization due to unitarity?
Sorry, can you say it again?
I'm trying to understand where does it consistent factorization come from? Is it come from the unitarity or locality or?
Oh, yeah, I would say it's really a signature of locality. By consistent factorization, all I mean is that on these partial energy singularities, that the correlator has the appropriate behavior, that it splits into a product of a sort of amplitude and a shifted correlator in the appropriate way with some pole structure. And that's really sort of it's a signature of locality. It's telling you something about particles coming together at a point. Whereas unitarity is a slightly different statement in this context. But if we get there, I can show you slightly more precisely.
Sure, thank you.
Or I can tell you afterwards.
Sure.
Okay. But the thing I'm going to sort of focus on is just the natural thing. Like if you have an object and you want to know how it changes when you deform it, the natural thing to do is to just find a differential equation that governs its amplitude under these deformations. Okay. And so I'm just going to try to explain briefly how you could find such a differential equation using as a guide the de Sitter symmetries of the background. Okay. So just as a very quick review, remember that in de Sitter space, the de Sitter group is basically the same as the group of conformal symmetries on a one-dimensional lower Euclidean space. And you can interpret that as really the action of the de Sitter symmetries on the late time space-like boundary of de Sitter space. Okay. And so it turns out that slow roll inflationary correlators are actually governed by the symmetries of de Sitter space, even though the interactions of the inflaton actually break these symmetries. Okay. And of course, kinematically, the de Sitter group is the same as the 3D Euclidean conformal group. So in cosmology, we always like to work in the inflationary slicing for obvious reasons. And in the inflationary slicing, of course, the 10 symmetries of de Sitter are sort of naturally realizable as the 3 rotations and translations of a spatial slice, which is just like an R3. And remember, in the inflationary slicing, this 3-dimensional space is just kind of getting bigger as time goes on. There's one slightly less obvious symmetry, which is just that if I do a time translation and rescale all my coordinates, it looks like I've done nothing. So there's this dilation symmetry, which just relates time translations and spatial rescalings. And then there are these 3 other symmetries, which are are kind of difficult to visualize in the bulk, but on the boundary, they just correspond to conformal transformations of the asymptotic future boundary. Okay. So for my purposes, the only fact you really need to know is that like I said, the de Sitter symmetry group is the same as the conformal group in one lower dimension. And this implies that late time correlations of fields in de Sitter space are constrained by the de Sitter symmetries in a similar way to CFT correlators. So this is almost exactly the same as what happens in ADS CFT. If I take a bulk field in de Sitter space and I expand it at late times, it will have these two characteristic fall-offs with time, sort of in the same way in ADS CFT, it has two characteristic fall-offs with radius. And these coefficients transform like conformal primaries, where the weight is just set by the mass of the bulk field through this sort of familiar ADS CFT relation, but with some analytically continued ADS length, if you like. Okay, so then what I can do is I can take the constraints of bulk de Sitter symmetry and translate them into kinematic ward identities satisfied by these late time correlation functions. And again, it's convenient for us to work in momentum space. And so if I do that, it turns out the really non-trivial ones are these dilation and SCT ward identities. The details are not particularly important, but you can sort of just see by staring at them that these are a set of differential equations that correlation functions have to satisfy. And in some sense, these differential equations are almost too general, because any possible like bulk process involving arbitrary loops and stuff like that will have to solve these differential equations. And so we sort of need some other information in order to pick out the solutions that we want. And one piece of information is that the singularities will provide boundary conditions for the solutions to these differential equations. And then, of course, as is very familiar, the 2- and 3-point functions are just completely fixed by symmetry in the de Sitter limit. And so the first non-trivial stuff really happens at 4 points, where you have a free function's worth of freedom. Okay. So in order to describe in a little bit more detail what the solutions look like, I have to first introduce some kinematics. So it turns out, remember the correlator that I'm interested in is in Fourier space. So it's a function of the shape of some quadrilateral in Fourier space, where the side lengths, of course, have to close to form a polygon. And it turns out to be useful to parameterize the shape of this quadrilateral, sort of like by the length of the diagonals relative to the length of the sides connected to them. And so I'm also going to restrict to kinematics where all of these points lie in a plane, which it turns out is not generic. But if I'm interested in the 4-point function that arises from the exchange of a scalar particle, actually this is general enough to capture all of those situations. And so in that particular case, everything can be reduced to a function of these two variables that I'll call W and V. Okay. And so then further, I'm going to additionally simplify things in order to write down manageable formulas. And I'm going to specialize to conformally coupled scalars on the external legs in de Sitter space. But I'm going to imagine that the particle being exchanged is sort of an arbitrary thing. Well, at this point, I'm not even saying anything about the exchange. I'm just saying I have 4 conformally coupled scalars making it to the boundary. I don't know what happened in the bulk, but the de Sitter symmetries tell me that that correlator has to satisfy this differential equation. So just by changing variables, you can see this is true. Where it turns out these delta operators are differential operators of the hypergeometric type. And so this differential equation, it's some PDE, is satisfied by all correlators of conformally coupled scalars in de Sitter. But of course, I care about some particular solutions, right? What I want are the solutions that correspond to the bulk de Sitter dynamics I'm interested in, things like the production and decay of some intermediate massive particle. Okay. And so there are sort of 3 sort of key ideas in order to extract the bulk de Sitter dynamics that I'm interested in from this differential equation. So the first one is that I can use the information that I know about what singularities this object should have in order to select the solution to this differential equation that has the properties I want. So I can either find something, that corresponds to a bulk contact interaction, or I can select the solution corresponding to the bulk exchange of a massive particle by demanding that it has the correct singularity structure. And so the first thing I'm going to focus on is to try to find a solution where a massive particle, a massive scalar particle, is exchanged between these conformally coupled scalars. And it turns out that once I've done that, basically all the difficult part is done. Because once I have that, I can use some simple operators in order to transmute this bulk scalar exchange solution into a solution involving the exchange of more complicated bulk fields. Okay, so that's sort of the second key idea, is that I can change the spin of the internal particle in a very simple and systematic way that I'll describe. And then the last thing is that, like Marcus was saying, I have been talking about the 4-point function, but what I care about for phenomenology would be the 3-point function. And so I need a way to transform this exactly de Sitter invariant 4-point function into a slow roll inflationary 3-point function, which I'll also say briefly how one does that. I am aware that it has been about an hour though. So if you want, I can try to wrap up relatively quickly.
How much would you have if you just kept going?
A pretty reasonable amount. So I don't think I'll get through all the slides no matter what, but maybe another 5 minutes, if that's okay.
Why don't we do this? Why don't you try to, if you can try to wrap up, because some people kind of have to leave. So why don't you try to see if you can wrap up some version of it in the next 5 minutes, and then some of us who can will stay a little bit later.
Yeah, totally.
How does that sound?
That sounds
We'll
great.
discuss what to do at that point. So why don't we do that?
Sure,
Okay?
sure. Yeah, that sounds great.
Thanks for being flexible.
Okay, cool. Yeah, okay, so I won't dwell on this too much then, but it turns out to be relatively easy to construct solutions that only have these sort of total energy contact-like singularities. It turns out, in fact, this thing that was already a solution in flat space for this special mass, it shouldn't be very surprising because it's a conformally coupled mass, continues to be a solution in de Sitter space. And then once you have this solution, if you just act with this kind of peculiar hypergeometric like operator over and over again, you just generate more solutions. And so you can think of this delta operator as being kind of like dual to a bulk derivative kind of expansion. So this just lets you in a simple way classify a huge number of bulk contact interactions. And then once you know that, you can use this information in order to construct solutions corresponding to particle exchange. And sort of the guiding philosophy is to try to find an operator that simplifies the singularity structure of the boundary correlator. So the boundary correlator for exchange, we expect will have all sorts of complicated singularities. It could possibly have cuts. It could have these partial energy singularities. It could be slightly complicated. And so the idea is to try to find an operator that when you act on that kind of complicated object, simplifies it such that the resulting object only has contact-like singularities. So that's sort of one perspective on how to go about inputting the type of singularity structure that you want in the solution. Another one is just to notice that if I handed you a solution of this differential equation, and if it also solves the analogous equation for V, then that thing automatically solves this differential equation, provided that C also solves that differential equation. So you can just kind of posit that the solution you're interested in solves this simpler ODE, and then you're guaranteed to find a solution to the PDE. And you can think of this fact that this thing collapses this thing into a contact correlator as the boundary version of the bulk fact that if I act on the Green's function with box, then I get the delta function. So you can really think of this thing as like box, and then what I'm generating is a contact correlator like that. And this is really an input of locality. The existence of some operator that simplifies the singularity structure you can think of as a reflection of bulk locality. Okay. So what we want to do is to solve this simpler problem, which is to solve this ODE. It's now a second order ODE of hypergeometric type, and so you can just totally solve it. It turns out I need two boundary conditions, unsurprisingly. One is I'm going to demand that the singularities are only in the kinematic configurations that I told you about. So there can only be a total energy singularity, and there can only be partial energy singularities. It turns out that a generic solution to this equation is also singular in this kind of funny limit where the quadrilateral degenerates to a triangle. And so it's sort of like a folded limit of a quadrilateral. It turns out that demanding that this singularity is not there is sort of the boundary reflection of choosing Bunch-Davies initial conditions in the bulk. And one way to think about that is that oftentimes when you choose non-Bunch-Davies initial conditions, you find singularities in these folded configurations. And so, yeah, so like I mentioned before, this is sort of where the information about Bunch-Davies initial conditions sneaks in. Okay. And then the other boundary condition is just we choose to normalize the partial energy singularity in the correct way. And then kind of like the simple example that I showed you, where demanding like consistent factorization of the partial energy singularities forced you to have a total energy singularity. Here, imposing those two boundary conditions actually forces the correlator to have a branch cut when the correlator collapses to kind of like a flat pancake. And it turns out that you know, as you approach this flat configuration, the amplitude of the correlator oscillates, and it turns out that it oscillates precisely you know, with a phase fixed by the mass of the exchange particle. And so if I kind of handed you this object, by inspecting this collapsed limit, you could infer the mass of the particle that was exchanged. Okay, so I won't show you the explicit solution F. It's like some terrible multivariable hypergeometric function, but you know, there totally exists a formula for it. You can solve everything exactly. So you can think of this object as just totally known. It's like a completely known function. And so once you know that function, it turns out that you can actually transform this function into the correlator that would arise from the exchange of spinning particles. So remember, this function is the thing that arises from the exchange of a massive particle in de Sitter. But you may be interested in situations where you produce like a massive spinning particle and that thing decays into inflatons or something like that. It turns out there's some nice technology developed in the conformal field theory literature that basically generates or transmutes the quantum numbers of operators in a CFT. And it works at the level of kinematics. And so for us, the kinematics are the same as a CFT. And so we can adapt these so-called weight shifting operators in order to transmute this scalar exchange correlator into a correlator for spinning exchange. Okay, and just schematically, it's takes some form like this where there's some simple differential operators you can work out that just act in an algorithmic way on this seed function that just generate the answer. And the reason that this is kind of interesting and useful is that it tells you there's like some universal part of exchange of massive particles in de Sitter, you know, that controls the singularity structure. And then there's sort of some stuff you add on that tells you about the spin and different masses and stuff like that. And this kind of cleanly separates those two things. And so if you're interested in doing data analysis or something like that, this like may suggest sort of an interesting and useful way of parameterizing the signal. Okay, so it sort of is the last thing that I will mention. So as I mentioned a couple times, everything I've just told you took place in exact de Sitter. But of course, we know inflation ends, so things don't take place in exact de Sitter. So what we really care about is what we really care about are correlation functions in some slow roll inflationary background, not in exact de Sitter. And then as Marcus was mentioning, you know, it's much easier to see a 3-point function than a 4-point function. So maybe we should care a little bit more about computing those things instead of the 4-point functions that I've been showing you. But it turns out that both of these things can be accounted for sort of at once. So given this 4-point object computed in exact de Sitter space, it turns out that by deforming the masses of the external particles a little bit and taking the limit where one of the momenta is taken to be soft, that actually this thing produces for you the 3-point function in a slow roll inflationary spacetime. And so there's a controlled way to deform this exactly de Sitter invariant 4-point object into a slow roll inflationary 3-point object. Okay. So maybe here is a reasonable place to stop. Maybe just as a summary, let me just say that sort of what I've been trying to emphasize to you is that taking sort of a boundary-centric philosophy on inflationary correlation functions can be useful, and that from this perspective, a sort of important role is played by the singularities of boundary correlation functions, and that getting a handle on these singularities sort of gives us a first sort of foothold in order to figure out how to extend away from these singularities, which can be done in more than one way. The way that I showed you in detail is to find a differential equation that controls the deformation of the correlator away from these singularities. But there are, in particular cases, other ways of doing this involving sort of factorization of rational correlators and things like that. But sort of the broader point that I want to make is that this emphasis on focusing on observable quantities, try to do everything in sort of as close to an on-shell type philosophy, appears to be fairly fruitful. And there's an interesting connection between correlation functions in de Sitter space and amplitudes in flat space. So it goes beyond just sort of being inspired by the amplitudes program. In a very precise sense, amplitudes live inside correlation functions. And so it stands to reason that many of the magical things that appear in scattering amplitudes have some echoes in correlation functions. And so we're just starting to see hints of those, but I think there are many more interesting things to discover. And I'll stop there.
All right. Let's thank Austin for a very nice talk. Unmute. So I kind of suggest my personal preference would be if we could just sort of talk informally a little more. Was that okay with you, Austin? Because
Yeah,
we're not really experts on this, you know what I mean? So I feel like, how do other people feel about that?
Well, that sounds good to me. I also have a couple questions if there's time about the talk.
Yeah, let's just, I think you may have to go, Rose, so why don't you go ahead and go first, because you said you had a time constraint.
Sure, that's fine. I do have a little bit more time, so if discussion evolves, I might be able to stay for some of it. But yeah, okay, a couple questions. First, your formalism depends like pretty much on the singularity in the infinite past and then propagating it forward. Do you, on like a big picture scale, worry that your methods might not be okay in like the very high UV, what some people call the trans-Planckian regime?
Yeah, so that is an interesting question. So in some sense, it's kind of related to this total energy singularity. So if you like, I argued that this total energy singularity is coming from the infinite past, like you say, where modes are kind of going to the UV. And you might be a little bit worried about that because you would say, okay, what I've done is I've written down some field theory into Sitter space. When I go to the deep UV, how do I even know that this field theory that I've written down makes any sense? Like, shouldn't I have to write down string theory or something like that?
Yeah.
And in some sense I do. So I think you can think of the total energy singularity as being like a field theory kind of UV divergence. And if you had sort of a model of string theory in de Sitter space that was very soft in the UV, your expectation would be that if I computed the analog of the Veneziano correlator in de Sitter space, that thing would not have a total energy singularity, that there would be some physics that came in and like softened the UV behavior such that it was actually totally regular in the total energy goes to zero limit. But at the level of like doing a field theory calculation, I think it's not any worse than what people do when they take the standard approach to inflationary perturbation theory, which is sort of assume that modes enter the EFT in the vacuum and then just do perturbation theory. So I think in that regard, it's the same, but there is a very interesting question about the UV, which is whether there exists an object that satisfies all the constraints that you would expect it to and does not have this total energy singularity, which would be sort of like the de Sitter analog of the Veneziano amplitude.
Well, thank you. That definitely gives me things to think about. I appreciate it. And I guess just in the interest of time, like one more question. You commented a little bit about like initial conditions and where like the sort of Bunch-Davies assumption sneaks in. I was wondering, well, two things, whichever's easier to answer. One, do all sort of non-Bunch-Davies states have that folded singularity, or are there some that are like essentially degenerate with like the Bunch-Davies choice? And second, have you investigated what the effect of having a folded singularity would have on sort of the final form of this like t equals 0 slice?
Yeah, good. These are both good questions. To be honest, I don't know if all possible non-Bunch-Davies vacua have folded singularities. I could believe that some of them don't, but it is in some sense generic. Yeah, to be honest, I'm not 100% sure. I could imagine you could cook up a state where some correlators look like they are the same as Bunch-Davies correlators, but if you were able to measure all possible correlation functions, for sure you'd be able to tell the difference. And my guess would be that at least one of these correlators would have a folded singularity, but I could be wrong. And then, sorry, the other question was, what if I instead like chose an alpha vacuum and asked what happened for correlators? Yeah, good. So that's an interesting question. From this sort of boundary perspective, it's sort of clear how you might imagine doing that. It would just correspond to choosing some different boundary conditions for this differential equation. So at that level, it's not particularly difficult. From the bulk perspective, my understanding is that people still kind of argue about whether or not things like alpha vacuum are actually well defined away from just tree level. So I don't know. Yeah, I don't want to. Yeah, I'm not an expert on it, so I don't want to comment too much about it. But we haven't thought very much about what happens if you move away from Bunch-Davies. Is sort of the short story.
Oh, but thank you. That answers my questions. And thank you for an excellent talk.
Yeah, thanks. My pleasure.